Today, I want to show you the output of one of my 2025 research projects, which was exploring macOS internals through Apple's open source software. This project focused on the collection of documentation in OSS code and how I went about doing that given Apple's secrecy. However, since AI has gotten good enough, I stopped using the manual version of this process, which I presented on last year, and so I also have blog posts on it and all of that. And in this presentation, I wanted to focus on one application of the results of this project, specifically AI workflows for vulnerability research. Before we begin, I want to mention a tool I published called OSS Sensor. OSS Sensor generates a prioritized evidence-backed research queue derived from Apple OSS diffs, basic binary features, and log templates. It applies custom rule-based scoring for supporting and triage. And the binary and log analysis components are intentionally lightweight. Intentionally lightweight, and there's no integrated LLM or vulnerability verification. It's designed as a triage and hypothesis generation aid, not as an automated vulnerability discovery or exploitation tool. There's currently two versions of this project available, one without built-in AI and one with AI capabilities. The non-AI version is more streamlined and significantly easier to adapt if you plan on integrating your own AI workflow. I strongly recommend this approach, particularly if you intend to iterate quickly or vibe code your enhancements, and this way it will be personalized to your setup and not dependent on how I set it up. That said, the PR for plug and play with AI API keys is still under review and testing, and admittedly, it's been under review and testing for a couple months. I don't plan on developing it further, and you'll see why. And this is because parts of my workflow, which this Talkin tool is inspired by, includes intentional manual intervention steps. While I was developing this process, I quickly learned that certain configurations become costly depending on usage. Thus, I'm unsure who might really want to have the plug-and-play version, especially if you're a beginner to the vulnerability research space on Apple's operating systems. And if you'd like to explore this tool, there's several built-in demos available. When connected to an AI coding agent, the tool will, outline the required execution steps and demonstrate scoring and weighing out of the box. The scoring is really important because, for me, for example, I really like tactile vulnerabilities and race conditions. It's something that I find easy to recognize. And if you're someone who's like, oh, I'm better with the explicit memory corruption space or something, you can adjust the scoring to fit what your vulnerability research profile looks like and what might be easier for you to navigate. And from there, you can incorporate your own AI workflow. Given the tool's simplicity and modular design, this is achievable within a few simple prompts. And in this talk, we will cover where AI has helped me in my research process and how I've influenced AI to better suit my needs, given that around a year or so ago, many AI chatbots couldn't tell you how to access logs on macOS. So in this talk, we're going to focus on a couple AI vulnerability research components, which are reverse engineering and fuzzing. Reverse engineering is inferring how a compiled system interacts and works from binaries and runtime behaviors, while fuzzing is automatically generating and mutating inputs to exercise surface and system invariance via crashes. My workflow tries to automate these steps in areas that I have found to be most reliable. First, the AI workflow treats Apple's open source code as a sensor. A sensor is any source that produces signals about a system, state, or change without doing the interpretation for you. Second, the workflow then uses AI agents to turn that sensor into a prioritized queue. So what changed, what looks security relevant, and what to reverse and what to fuzz. For context, an agent is a system that can take goals, select tools, run steps, and produce structured outputs. The problem is that Apple ships a huge security surface area, but only some of it is open source. Apple has over 400 public repos, but these releases are incomplete and it's very hard to keep up with manually. So my time, as a result, is limited by bandwidth. Thus, the story I'm going to tell is diff to hypothesis to harness, and the trick is we augment open source diffs with two other signals, binaries and logs. Now, I want to address the elephant in the room, which is Apple's secrecy. I have a bunch of blog posts on this too, with how I go about mitigating that. That said, Apple actually open sources more than most people expect. The X and U kernel core libraries like libsystem, libc, and libdispatch, and historically some daemons like launchd. but they don't publish everything. Some components are missing or only partially available, including things like Core Foundation, CF Network, iOS-specific drivers, pieces of Dialog, and Core Crypto, which also comes with additional redistribution constraints. Also, source drops can be incomplete or outdated. You'll see headers referencing files that do not exist or build instructions missing. And for context on the constraints and why this workflow matters operationally, a little bit of self-promo here, but I recommend watching my B-Sides 312 talk where I cover the history manual version of the process I'm about to describe. So, what does this have to do with AI? This information overload with Apple's 400 plus open source repos is exactly why agents help in this context. If I rely on a human, aka myself, doing manual repo exploration and one-off diffs, I end up with a very narrow view of risk. If I automate that bookkeeping, I can spend more time on the parts AI is not working well for me yet, which is reasoning about privilege boundaries and exploitability. I've even found this to be helpful with localized threat detection engineering, and this matters because the faster I can build detections and I can understand what changed, I can understand, what the new attack mechanics are, and I can adjust as soon as I understand what changed. So it kind of creates this cycle. And even though the code is incomplete, it still guides my research. The key is for both me and AI to treat it like a map. I might not have the full territory, but the landmarks are real. And what I do and what many other researchers do is use Apple's open source as a reference while working with the proprietary binaries. You'll take a binary like launched, syslogd, or a driver, which are all demos used in OSS Sensor, or whatever source that you decide to choose, and you can match known functions, annotate call patterns, and reverse unknown logic. Here, the agent angle is simple, but this hybrid method, it's effective and doesn't scale. So agents, they can do these repetitive steps, which is, correlate symbols, chase string anchors, retrieve relevant source context, and produce structured summaries that make a human reviewer faster and more consistent. Even when symbols are stripped, structure plus syscall usage plus string constants lets you map back to open source code. And 4 common tools will show up constantly. So strings will give you debug messages, format strings, and file paths. What can extract version and project info. Then there's NM, which lists symbols, like the symbol names if they exist, especially in unstripped binaries or frameworks. And then class dump is great for interface information, especially private frameworks and Objective-C method surfaces. And when I'm trying to map binaries to source projects, I also use Apple's distribution manifest to cross-reference components per release. I look at the release metadata when it exists, and I look for version strings or source file names via strings or what. All of these repetitive but context-dependent steps are the exact operation I hand to an agent as tools. I don't want the model inventing facts. I want it calling strings, parsing the output, then retrieving the corresponding source chunks, and then producing a bounded conclusion about what it observed with the citations. After this, I usually want to go deeper with something known as binary diffing, which is comparing binaries before and after a patch to identify changes. And here is my favorite example of this. So in 2016, OS X Reverser used Diaphora to diff syslogd from version 10.11.2 to 10.11.3. He found that only one function had changed, and that was an allocation math fix. Value plus 4 became value times 4 plus 4. From an exploitation mindset, this is suspicious because it looks like a heap overflow mitigation. And there was a string nearby that stated add lockdown session realloc failed, and that was a hint back to the source. This kind of surgical diffing is how vulnerabilities get reversed after a patch, and it matters because fixes often need to be applied in multiple locations. If identical code is patched in some files but not in others, the unpatched ones can remain vulnerable. And the larger and more bureaucratic an organization is, you better bet there's going to be repeat mistakes in neighboring files, specifically in neighboring files of their products. Now, imagine this exact AI workflow running continuously on every Apple release. It would ingest the new OSS tags or tarballs and distribution manifests and compute diffs at the function and semantic level. Then it would score changes for security relevance based on patterns like allocation math, bounds checks, entitlement gating, XPC parsing, and IOKit external method table changes. It would correlate to binaries and string anchors, then emit a ranked queue with why this looks risky, plus pointers for a human to validate. And for my solo offensive research, this was a throughput multiplier. I've only tested this on small individual components and never on the full OS, but it would be awesome if I could expand it to something like that. And for an organization, this would compress the loop from, Apple just shipped something to we've identified the shifted surfaces and behaviors so we can adjust focus, monitoring, and triage faster. I'd imagine if this was scaled, this is the kind of workflow you'd expect from a dedicated vulnerability research team rather than a random lady with a computer. And that's why I think this is worth discussing openly. It helps keep vulnerability discovery accessible to the junior engineer, which is me. So here's the architecture I've had the best results with. First, I use an agent pipeline approach, which means that I'm using a coordinated set of tool-using agents that turns raw input, so diffs, binaries, and logs, into evidence-backed outputs like a ranked triage queue, hypotheses, and then fuzz/telemetry plans. I start by using a retriever. This is the indexing layer that searches embedded information like OSS code, symbols, notes, and log templates to return the most relevant context for a given question or artifact. Then I use a toolbox, which is a curated set of deterministic analyzers and system commands like strings, OTool, class dump, and log queries that the agents call to gather facts and generate evidence instead of just randomly guessing. And then more agents handle things. I use different agents for diff triage, RE context, hypothesizing, planning, and analysis. I'm unable to tell you which are most effective, and I'll explain more on how I account for that later. I don't, treat this model as some sort of god or whatever. I treat it as an assistant, since I'm a junior engineer and don't, always know what I'm talking about, right? It can, read fast, follow procedures, and generate structured hypotheses that we can validate with reversing, tracing, and fuzzing. Additionally, it is important to remember that each step in itself can break, and they're all depending on each other. Thus, your setup should ideally account for that, since you might be on a paid personal plan with limited resources. The big addition to this talk versus the classic I used Apple OSS to reverse stuff is logs. Unified logging gives you subsystem and category labels that map to components, stable message strings that you can hunt, and binaries and source, and execution hints that you can use as a pivot point into attack surfaces and code paths, not as doctrine due to bulk that I don't always know how to handle. And for reference, if you're wondering what I mean by bulk, if you just run unified logging on your machine for a second, you'll have over 100 unique distinct logs. So that's the type of bulk I'm talking about trying to narrow down. So these logs, they're good at telling you which components actually handled the input, often via subsystem or category plus sender image info, and what error paths fired that can reveal parsing assumptions, type expectations, and IPC contracts. And in my opinion, that's pretty good ROI for target selection, harness design, and the general question of what to fuzz next. An AI agent, in general, can do 3 useful bounded tasks with logs. First, it can take a log line and find where that string lives in a binary via strings and then locate its basic block and callers. Next, it can retrieve adjacent OSS code for those callers if it exists and produce a structured summary like inputs, trust boundaries, and parsing. Lastly, it can feed that summary into fuzz planning or into detection engineering, like what to watch, what parameters are attacker controlled, and what failure modes might look like. And this is relevant to developing POCs as well as localized endpoint detections or tests. When your AI research pipeline learns a new trusted input boundary or a new privilege XPC entry point, you can translate it into telemetry requirements and correlation rules. And in general, that's how you turn vulnerability research into coverage, only in the past, we just did it without AI. The same idea kind of applies to those back in the day kernel extensions. By diffing KX across various versions, researchers have found changes to external method tables that surface newer patched entry points and IOKit drivers. Now, getting back to the agent pipeline, what the AI Fuzz Planner agent produces is not an exploit unless you made it do that somehow, if you have access to offensive models and all of that. It's in this case, it's a plan. First, it enumerates candidate surfaces like syscall handlers, IOKit user clients, XPC services, and parsers, so you can focus on the entry points where attacker-controlled inputs actually cross trust boundaries. Then it proposes a minimal test driver or harness scaffold, including the invocation path, entitlement requirements, and expected input shape, so the target is reachable and reproducible at scale. And here, scale just means repeatability, since if you're trying to get money or sell your findings, you're going to have to prove that you can do it. So you have to be able to repeat it. Next, the AI recommends a seed strategy by extracting dictionaries from strings, mining parameters from logs, or bootstrapping from observed traffic so coverage ramps quickly instead of mutating from nothing. Note that if the command is not available in the subset that I provided, you can add them yourself or connect an AI search chatbot so that it can find those commands automatically. That said, I do not recommend allowing AIs to search the internet and then run things on your machine. If you're on a machine that is not solely for testing purposes especially, I'm in the lucky position where I have multiple versions of each Mac and all that, so I'm able to have the compute power to do that, but it's not really something I recommend. Also, back to the seed strategy I was talking about, this is a method for selecting and generating the initial set of representative inputs that bootstraps a fuzzer's coverage and guides mutations towards a high-value code path. Finally, the AI defines success metrics like crash bucketing, sanitizer signals, and unique stack traces so you can identify progress and turn results, ideally, into actionable research. Where this AI workflow breaks down today is when you ask for full exploit chains. To be honest, I'm not at the point in my research career where I'm finding those 7-chain exploit 0-day, things, like full privilege escalations and disabling all the security controls on Mac. Additionally, I've spent significant time just trying to understand and test how the operating system is working, and this knowledge is great for that learning by doing approach in general. That said, the models will occasionally invent steps, especially if you hook up an AI chatbot, so I keep it constrained. So bug class prediction and harness design are the high-value outputs, and then humans own exploitability. This also keeps the larger AI models happy, given that a lot of them try to put mechanisms to lock them down even for offensive purposes. And if you're like me and don't fully trust your first pass instincts, it helps to sanity check ideas against high quality public works. For example, Patrick Wörtle has an extensive body of writing, and I use AI tooling to check whether my hypotheses line up with these established techniques, as well as his published analysis in my own notes. This isn't wired into the OSS project yet, but I might add it since I do these sanity checks quite frequently. The TLDR of how I do this is I just create a folder in the repo I'm working in, and I just put the files, the blog posts, the PDFs of them in that folder, and then I just add that to whatever chat I'm using. So hopefully I don't need to add it to the project, but, because you're just creating a folder, but that's how that works. Also, credit where it's due, I intentionally license OSS Sensor GPL-v3 because I learned a lot from GPL-v3 license work by Patrick's and many others. By keeping the code shareable, it helps others build and learn the same way. The TLDR, though, is even partial source is powerful. If you combine it with binary analysis, you can reverse Apple's subsystems with surprising accuracy. But there are constraints: incomplete OSS releases, obfuscation, and licensing. You need a pipeline that is compliant by design, so local indexing, careful handling of source drops, and provenance tracking so that you can explain every conclusion. All of that said, what did we learn? So the core idea I wanted to leave you with is that Apple's partial open source code can be treated like a sensor stream. It's not the full system, but it's a steady source of change signals, and those signals become much more valuable when you can process them continuously. The workflow I shared takes that sensor and turns it into a prioritized research queue using AI agents, but with a very specific philosophy. The model's not God, it's a tool using, junior analysts. The work happens in deterministic tooling, and the model's job is to stitch together evidence, retrieve the right context, and produce structured outputs that make a human reviewer faster and more consistent. And that's why the narrative is diff to hypothesis to harness. You start with a diff, source or binary, and then you ask what meaningfully changed and where that trust boundary might be. And then you turn that into a testable hypothesis about a bug class. It can help with size calculation issues, parsing assumptions, policy gating, and interface surface shift. And then you build a minimal test driver so that the path is reachable and reproducible, which sets you up for fuzzing and validation. The trick is that open source diffs alone is not enough, so we augment it with two other signals: binaries, because they reflect the reality that ships, and OS logs, because unified logging is a good ROI pivot into which components actually handled the input and which error paths fired. The fuzz planner piece is an example of how this stays practical and bounded. It doesn't generate an exploit, it generates a plan. It tells you which surfaces matter, how to reach them with a minimal harness, how to seed inputs so coverage ramps quickly, and how to measure results so that you can identify findings. And importantly, it acknowledges the limits. Open source releases are incomplete, binaries can be opaque, and models can hallucinate. And that's why everything in this structure is evidence-backed, provenance-tracked, and compliant by design. So I personally stopped throughout this process. And this is why I can't tell you necessarily which models work and don't, but I've utilized AI tools like ChatGPT's deep research, but given the cost constraints, manual review is required for me, especially if it looks like something I won't understand. Given these AI systems are great but also hallucinate, and given that I might not always know what I'm talking about, it is imperative for my research to have manual checks. For example, I spent around a month processing Apple's open source repos. I spent around $3,000. That's like a rent payment, you know? And when you're not tracking that type of stuff, you're like, oh, I just spent a lot of money. And the reason I mentioned like ChatGPT and all that stuff is that, you know, I recently graduated and ChatGPT was the first thing that came out, so that all the students were like, wow, that's so cool. So of course that was the first thing I used to start doing my vulnerability research. And let me tell you, 4.0 came out, I was like, this is great. And then every update after that, everything just got garbage, super garbage. And I said this publicly, and then they got upset. And so that's why I realized that I need to be a little bit more careful with the things that I say in general. So, but yeah, I have found that switching to Gemini was a huge cost saver, and it's a lot more accurate too. I'm assuming that's because Google maybe started off as a search engine, and I don't need to use the pro models as much. Also, this is not just an offensive research like productivity hack. The same pipeline shortens the loop for localized threat detection engineering. When you can quickly identify what changed, which behaviors and interfaces moved, you can update monitoring, prioritization, and triage faster in platform churn into detection coverage. And yeah, so these are the outcomes I care about, which is making macOS vulnerability research more scalable, more teachable, and more operationally useful. So I have more in terms of where you can go from here. I released an Apple security newsletter. It's called Ret to Read. I released this after I graduated. I post approximately once a month or every other month about my research. So yeah, thank you so much for providing me the opportunity to present. I hope you all enjoyed. If you have any questions, please let me know. I'm an open book. So there we go. Thank you.